The title of this paper is Semi-Supervised Learning of Optical Flow by FlowSupervisor. I'm Ubin Im, and I collaborated with Sebin Lee and Professor Yoon. Optical flow can describe motion in a video. This video shows optical flow fields being overlaid on video frames. Specifically, optical flow is the displacement vector for each pixel. In this frame, you can notice that each pixel's color represents the magnitude and direction of a motion. Suppose we want to train a deep optical flow model on a target dataset. In that case, a standard pipeline is pre-training followed by fine-tuning. For instance, we have large-scale synthetic datasets such as chairs and things, and we pre-train the network on these datasets. We fine-tune the deep network on the labeled target dataset, and we can achieve good accuracy on the target dataset. However, we can't use the supervised fine-tuning if we don't have the label on the target dataset. Then, how can you get better accuracy on the target dataset without a label? This graph shows the pre-training step and the error on the target dataset, Sintel. In this case, we can possibly choose the conventional unsupervised loss. However, it doesn't improve the pre-trained network on the target dataset as seen in this graph. Thus, in this paper, we propose to use our FlowSupervisor to minimize errors in the target domain. In this case, we use both the labeled and unlabeled datasets. It results in semi-supervised fine-tuning, which is better than the other method. We use a self-supervision framework with a student and a teacher network. Here, the teacher network predicts a pseudo-label and is used to update the student network if the ground truth is not available. The structure of FlowSupervisor is based on the self-supervision framework, and we made several modifications to the structure. We have a student network which predicts optical flow y hat from input x, and the teacher network is used to supervise the student network. In previous methods, the parameter of the teacher network used to be shared, fixed, or moving averaged. Instead, we introduced FlowSupervisor as a separate module. FlowSupervisor aims to correct errors in the predicted flow and provide a good supervision signal to the student network. Thus, we use the student output connection. The predicted flow is fed to FlowSupervisor, which learns the conditional knowledge y given y hat. FlowSupervisor predicts the residual flow, which estimates the errors in the predicted flow y hat. The residual flow is added to the predicted flow and becomes the teacher output. In this structure, the residual flow, the output of FlowSupervisor, is used when updating student parameter data. This equation holds when we use the squared loss function to minimize the difference between the predicted flow and the teacher output. This is the general structure of optical flow self-supervision, and we add these modules to the architecture. In the optimization step, we use both the labeled and unlabeled datasets. The loss function is the summation of the supervised and the self-supervised loss. We can observe a clear improvement when we compare FlowSupervisor with the baseline self-supervision method. In this experiment, we use the labels from the synthetic datasets. On the other hand, we use no labels from the target datasets. The bar charts show that our semi-supervised method can improve over the supervised baseline on both Sintel and Kitty datasets. Also, we can use our semi-supervised method even when we have labels on the target dataset. In this case, we use additional unlabeled samples related to each target dataset. The bar charts show that our method is effective in this case too. Lastly, we want to show some research from the Davis dataset, which does not have optical flow ground truth. In this figure, each column shows respectively input images, supervised only case, and ours semi-supervised case. As seen in the marked regions, ours improves over the supervised only approach. Thank you for watching, and visit our project page for more research and code.